Okay. So searching. Like I said last time, searching we mean seeing if something exists in a collection of things. And we're going to use needle and haystack. Haystack is the thing we're searching through. Needle is the thing we're looking for. And we can talk about a linear search. Linear search, start at the beginning of haystack, sequentially go through each thing, checking if each thing is the thing I'm looking for. As soon as I find it, I can conclude it's there. But if I haven't found it yet, I keep going. And I'll keep going until I find it. Or if I get to the end and I never found it, what do I then conclude? It's not there. Right? That's a linear search. This shouldn't be new. We've been doing this since like mid-161. Notice that the description of this algorithm doesn't go into any more details. The algorithm description is start at the beginning, look at each thing. Is it what you're looking for? Yes or no? If not, keep going until you get to the end and you don't find it's not there. That algorithm, I could go tell to a 5-year-old and they can do it. It's an algorithm. It's a set of instructions. It's not Java code, it's not Python code, it's not code, but it's still an algorithm, right? Remember that. It's an important thing to keep in mind. Algorithms aren't these overly complex things. I'm not being silly when I say following a recipe is following an algorithm. It is. I'm not being like, well, technically by definition, no, it's not even that. It's just it very intuitively is an algorithm. Following directions to get from point A to point B is an algorithm. Even if it's not code. Code has nothing to do with whether or not something is an algorithm. All right. So computation complexity of this algorithm is linear. Why? Well, we think worst case scenario. Worst case scenario, the thing you're looking for is the last element or it's not even there. So best case scenario is if this is the set of numbers I have, they happen to be sorted. Best case scenario is the thing I'm looking for is the very first thing. If I'm looking for 1, all right, the first thing is 1. Is that what I'm looking for? Yeah, oh, done, there, found it. Easy peasy, it's there. But worst case scenario is it's at the end, meaning I gotta go look at all n things where n is the length of that list. And if it's not even in there, well, I still have to look at n things. And on average, we're not going to get overly formal talking about like the average computational complexity, but you figure on average, imagine I took these numbers and I shuffled them, and I'm always looking for the number 1. I shuffle them, look for 1, shuffle them, look for 1, shuffle them, look for 1. On average, that 1 is going to be like in the middle, right? Because for every time it's the first element, there'll be another shuffle where it's the last element. For every time it's the second element, there'll be a time it's the second last element, and so on. So on average, it's like half, which would be like n over 2, but of course, that's just a coefficient. We don't care about those, so on average, it's still linear time. Yeah, right? So there's my set of numbers. They just happen to be sorted. That's not important for a linear search. It's just this collection of numbers is sorted. Now, one thing I want to note here, and this goes back to what we were talking about at the very end of last lecture. One thing I want to note is every time with a linear search, I look at the number 1. Let's say I'm looking for the number 15. It doesn't really matter what I'm looking for, but I'm looking for a number that's not 1. And I look at the first element and it's a 1. And I conclude that's not what I'm looking for. I have n elements in this list. By looking at one thing and concluding that that thing is not what I'm looking for, how many of those n elements that are there did I eliminate from my search? This isn't a trick question. If you're second guessing yourself, you're thinking it's a trick question. It really is a simple answer. I looked at one thing. 1 is not the number I'm looking for. So how many things did I eliminate from my search? 1. Only 1. There's nothing wrong with that, but I eliminated one thing. Now here's a generic implementation of some linear search. This should not look shocking in any way. If it is, I don't know what you're doing here. Assuming I have some constant not found, iterative linear search takes a needle, takes a haystack. The haystack is just some array. It could be whatever, but let's just have it an array. Go to the end of the array, start at index 0 if the thing I'm looking for is the thing I'm looking for. In this particular case, it looks like I'm returning the integer, the index of that thing, not true or false, but close enough. So if I find it at any given index, return that index. If I ever get to the end, I'll return some special not found value. Linear search. Start at index 0, go all the way to whatever the length of the array is. Any questions about this? Should be fairly straightforward. Think of what the algorithm is saying. Start by looking at the first thing. Is it what you're looking for? Yes or no? No? Look at the next thing. Look at the next thing. That's the algorithm. This is an implementation of that algorithm. It's an iterative implementation in Java. The iterative implementation is fairly similar to the high-level description. Start at I equals 0, the beginning of the haystack. If the element is at index I, is what you're looking for, you conclude it's there, you're done. Otherwise, continue and increment I. If the end of the haystack is reached without finding the needle, then we conclude that it must not be there. Right? Now, here's a recursive implementation. Let's talk about it. It takes 3 values as parameters. Takes the needle, the haystack, and some current index. I would call this with starting at index 0. Current index would be 0. Because that's where I want to start. And let's look at what the code says. If the current index is equal to the length of the haystack, you're done. It's not there. Okay? So if let's say haystack is empty. There's 0 things in it. You start the search. What's at index 0? Well, I don't care. There's no index 0. It's not there. The more general case, I have an array of size 10. If I try to get to the current index being 10, remember there is no index 10 in an array of size 10, 0 through 9. So if I ever have my current index at the end, that'll mean I reached the end. And if I reach the end, and I never found it, it must not be there. But maybe I'm getting ahead of myself. Okay, if current index is the length, return not found. If object equals, if the thing in haystack at current index is the thing I'm looking for, if it's the needle, I found it. So imagine here I've got that list, I'm looking for 1. And I say, okay, is haystack at index 0, 1? Well, it is. Return current index. Current index is the index where it exists. Otherwise, if we're not at the end, if we haven't found it, what do? Continue searching. And I do that by calling the recursive linear search. But this time, I'm going to keep looking for needle. I'm going to keep looking through haystack. But this time, the index I want to look at is the next one. If current index is some arbitrary value, I want to look at the next one, which will be current index plus 1. If current index is 0, and I didn't find it, and it's not the end, do a recursive search, but on index 1. If I found it, good. If I'm at the end, I'm done. It's not there. Otherwise, do it again, but on current index plus 1. Well, now it would be 2. And so on. So this is a recursive algorithm. It might seem very different than the iterative implementation. And obviously, the code implementation is different. One's iterative, one's recursive. But the algorithm is identical. The underlying algorithm is the same. Start at the beginning. Is it what you're looking for? If it is, you're done. Are you at the end? No. Keep going. Start at current index at 0. If the end of haystack is reached without finding a needle, then conclude that it's not there. If the element at index current index is the needle, then conclude that it is there. Otherwise, keep searching at the next index. It's the same algorithm. The code is different, but the code is different from the algorithm. They're not the same thing. The algorithm is the idea, the set of instructions you're going to follow. The code is how you encode that algorithm, but you can encode it however you want. It's the exact same algorithm, but the implementations are different. If you're struggling with this, let's talk about it. Do we have any questions about this recursive one? Yes?
This would be more useful to use for like a sorted list, wouldn't it?
Why?
Because you could start current index right in the middle by taking the length and then divide by 2.
Why though?
Well, say if it's alphabetically sorted, you're looking for an S, like something that starts with an S first, and it's already sorted, then you can just go halfway through and then
So-
it would reduce N.
I see what you're saying. Now, what you're describing is a different algorithm. It's still a search algorithm. It'll still do the same thing, but the algorithm is different. Because the linear search algorithm is start at one end, go to the other while looking for what you're looking for. What you're saying is closer to that book, that textbook I have. Does anyone in here, do you have your textbook still? Can I take it back? It's not in the plastic this time. Money well spent, right? Yeah. I'm really glad you spent the money, because now I have a book. I'm looking for page 300, let's say. Okay? I'm looking at page 356. The reason I started in the middle was because I knew this book had like 600 pages. So I'm going to guess that the thing I'm looking for is going to be somewhere in the middle. Let me take a step back. I give you this book and I tell you to turn to page 300. I'm going to tell you exactly what you're not going to do. You're not going to do this. This is ridiculous. It's ridiculous because you know that there's a lot of time wasted in between here. I'm on page 15, 16, 17. 18, 9. I'm nowhere near 300. You know I could go like this. Now I'm looking at page 398 this time. Okay? So I turned to page 398. When I was doing it like this is page 23, 24, 25. Every time I look at a page, I eliminated one page from my search. Is this 3? No, it's not 300, not 300, not 300, not 300, not 300. I'm eliminating one page. Every time I look at a page, I don't need to look at it anymore because I concluded it's not there. But this is a little different. I turn to page 398. All the pages less than 398 are over here. All the pages greater than 398 are over here. Do I care at all about this half of the book? I said half, roughly half. Why do I not care to look through here anymore?
300 is less than 398.
300 must be here. It must be. Because 300 is less than 398, and that's how numbers work. It's not over here because, well, it's less than. How many pages did I eliminate from my search? Hell of a lot more than one, right? Let's say roughly half. It's really not, but let's say. Be generous to me. So I'm going to search again, and I'm going to go here. Ooh, I got pretty close. Too close. I'm going to pretend I didn't turn there. I'm at page Shoot, I should have kept this. 398. There. I turn to page 292. I'm pretty close to 300, right? All the pages less than 292 are here. All the pages greater than 292, but less than 398 are in here. Where do I continue the search? In here, right? How many pages did I eliminate with one question? Hell of a lot more than one page. Every time I look, I eliminate more than one thing. But there is a giant catch. This only works in a very special situation. Can you tell me what that situation is?
It's whenever, like, you have to have different if-else statements.
Well, that might be what's in the code, but what must be true about the data I'm looking through? About the collection of things I'm searching through, what must be the case? There's a lot of hands up, so let's see. Who do I want to ask? Let's go with you.
Oh, they have to be in like order of like say numerically.
They have to be ordered. It's like playing hot or cold, or higher or lower. Like if I told you, you know what? I'm going to have a quick look through my code for my computer for a second. I'm going to see if I can find some code real quick. If I can't, well, I'll give up real quick. If you're watching this on YouTube later, you'll see everything I'm doing, so. All right, I don't have the code, but I can do it. It'll just be a little slower. All right. If I were to tell you to pick a number between 1 and 1024.
24.
Well, don't tell me.
512.
Don't tell me. So, if I told you to do that, and I were to say, okay, is 1 the number? You're going to say no. Is 2 the number? Is 3 the number? Is 4 the number? How many guesses, worst case scenario, is it going to take? 1024. But if I do this, okay, someone pick a number, but don't say it. Someone pick a number and raise your hand if you've got a number in your head. I want someone different. I want you. Okay, you. You've got a number. Okay? Okay, I'm going to get, but there's a catch. Okay? I'm going to promise you I'm going to get it in no more than 10 guesses. Okay? Is the number 512?
No.
No. Now, you got to tell me though. There's just one little thing you got to give me. Is it higher or lower?
Higher.
It's higher. Okay. So, is it 768?
No.
Higher. Is it 896?
No.
Higher. Is it 960?
No. Higher.
Is it 992?
No. Higher.
No higher. Is it a 1008?
No. Lower.
No, lower. Okay, hold on. I gotta, now you're making my life difficult. Is it 1000?
No. Lower.
No, lower. Is it 996?
No. Higher.
No higher. Well, I think I know what it is, but I'm going to just keep going. 998?
No, lower.
No, lower. Oh, you're making this up. You don't have a number, do you?
Then 998.
Well, my last guess then is 997.
Yeah.
There it is. 997. And that was exactly 10 guesses. Okay? But if I did a linear search, that would have taken me 997 guesses. But I did it in 10. In fact, I'll tell you that if I doubled the number of numbers to 2048, I would have been able to get it in one more guess. I would have only needed 11 guesses, worst case scenario. And if you doubled it again, I'd only need one more guess. Every time you double the possible range value, I only need one more guess. And it should be fairly intuitive why. If you don't believe me, listen. Every guess, every one guess I make, how many numbers do I eliminate? Half. So you could double it, and with one more guess, I'll eliminate that double. Any questions about that? Now, if it wasn't obvious what I was doing, I started by picking a number right in the middle. 512. It was right in the center of 1 to 1024, right? And then he said higher. So I took that number and added, I found what was halfway between 512 and 1024, which was 700 and whatever. That was the process. Every time I just took half of the difference and went in between. That was the trick. Every time I'm eliminating half the things. So a binary search. Imagine looking for page 5. Yeah, okay, I just worked through it. Great. So here's kind of how we could think about doing this is what we call a binary search. What I was doing here with the book is more general, like an interpolation search, but the particular one I'm doing is a binary that's like halving every time. It's more systematic, let's say. But this is how we could visualize that. If I'm guessing a number between 1 and 15, I'd start by guessing 8. Someone pick a number, let's visualize this. Someone pick a number in their head between 1 and 15. Okay? Who's got that in their head? Let's go with you. You've got your number. Okay, is it 8? Is it higher or lower? Okay. So I don't care about that right-hand side anymore. It's gone. Is it 4? Higher or lower?
Higher.
Is it 6? It is. Great. If it was 7 or 5, I'd only need one more guess. But that would be the worst case scenario. It's going all the way down this like tree. We call things that look like this a tree. Sure, it's upside down, whatever, deal with it. Best case scenario, it's 8. Worst case scenario, I gotta go all the way down a tree. But I can't go any lower. That's the idea of a binary search. Now, how do we do this? Now, okay, actually, let's talk about the complexity of this. Linear search, it's linear time. Binary search, worst case scenario, how many guesses do I have to make? If this was linear, worst case scenario is I'd have to make 15 guesses. Here, worst case scenario is 1, 2, 3, 4 guesses. 4 is a hell of a lot less than n. If I doubled it, if this was 30, I'd only need one more guess. As n gets bigger and bigger and bigger and bigger and bigger, I can double n. It still only gives you one more guess, meaning the amount of guesses I get grows way slower than n. Nowhere near n. It's not linear. It's way better than linear. Who can give a shot at what the computation complexity of it is? Log base 2, is that what you were going to say?
Yeah.
Raise your hand if you were thinking that. Raise your hand if you were thinking square root. Good, because you don't see that very often. Why is it log base 2? Well, remember, log is like the opposite of to the power. So dividing by 2 multiple times, that's log base 2. How many things will log base 2 event? Every time I make a guess, I eliminate half. In reality, every time I make a guess, I actually eliminate a little more than half, right? Because I eliminate 8 plus everything on the right-hand side. So it's actually a little better than that, but whatever, we're lazy. We'll say, it's log base 2, it's like half. So this is way better. But of course, this comes with a giant asterisk, and it's that the data I have must be sorted. It doesn't need to be sequential like this. The data does not need to be sequential. Even though the examples I did were sequential, meaning 1, 2, 3, 4, 5, it doesn't need to be sequential. All that it matters is that it's ordered. And it has that well-defined ordering. Okay? Sorted. Let's say sorted. So, okay. That's why we end up with a way better algorithm. If I give you an algorithm to solve a problem that's linear, and another algorithm that's going to solve the exact same problem that's log base 2, you take the log base 2 one. It's way better. But that's not always going to work. So if you're asking the question, why is that other algorithm so much better? It's because we can exploit what we know about the data. It's sorted, and we can use that to our advantage. When the data is not sorted, you can't do this. You cannot do a binary search on unsorted data. It won't work. Because as soon as I say, was it higher or lower, it's an irrelevant question. Because you don't know where it would be. How often do you have sorted data? I don't know, it kind of depends. Depends on the problem. Maybe you get data that's already sorted. Maybe you got a bunch of data. So that really, all you got to do is sort the data. Right? All you have to do is sort the data. If I gave you a billion pieces of data and told you you're going to be searching through this a lot, maybe it'd be smart to sort it. And then it's good to go every time you want to do a search for something. It's sorted, you can do a binary search way better. Awesome. But how do we sort things? Is sorting easy or hard? I don't know. Okay, let's think of how we analyze this. By talking to the log base 2 thing, we came up with a very intuitive approach to understanding it, which is good. We're halving every time. Look for an element. Looking for the element at the bottom would be the worst case scenario. Okay, yeah, we basically just did this. Great. All right, cool. Let's look at an iterative. Oh, I think that we got an issue here. We're missing the function signature. That could be fixed. Here's an iterative minus the signature of the function. The function's probably just called iterative binary search. Here's an iterative binary search. Start with the low index at 0, the high index at the length of the array, and the midpoint is, well, the midpoint between the low and the high, calculated with very simple arithmetic. I asked the question, okay, well, low index is less than high index. Well, okay, yeah. If haystack at the midpoint compared to the needle is 0, remember with compared to, if it's 0, they're equal, right? If one's less than or greater than, that's when we get like a positive number and a negative number. If it's 0, they're equal. And this is how you would do a comparison typically on things that have comparable implemented. This must be the case because this data must be sorted for this algorithm to work. So there must be orderedness to it. So if the thing at the midpoint is what I'm looking for, we're done. If it's not, we ask higher or lower. Okay? That's what's going on lines 34 and I guess 37 with the else. If it's higher, then, I guess if it's lower, then the high point becomes the midpoint minus 1. No sense in including the midpoint anymore, right? I have all this data. Let's say this is the lower end, 0 length, midpoint. If the thing I'm looking for is over here, well then set the new high point to midpoint minus 1. If it's greater than, do the same thing but midpoint plus 1, but with the low end. And you just keep doing this iteratively. The recursive one, once again it's missing the signature. The recursive one might look a little crazy here, but it actually, to me, has that nice, beautifulness you get with recursive algorithms. If low index happens to be greater than or equal to the high index, meaning if you've ever somehow crossed these things, you're done. It's not found. Otherwise, get the midpoint. By presumably low index and high index would be parameters for this algorithm. They're just missing because I messed up on the website. Calculate the midpoint. We're doing that same thing we did in the iterative. If it's what you're looking for, you're done. Otherwit's continue the search on the upper half or lower half, depending on where it was. It's exactly the same algorithm as the iterative. It's the same algorithm. The implementation is different. The algorithm is the same. And it's the same because this recursive call is a thing saying like continue the search but on this subproblem. Right? The big point I'm making here is, like, look, these are non-trivial algorithms. If I'm talking about this recursive binary search and you don't understand it 110% right now, you're normal. I'm not expecting you to look at this and be like, yeah, it makes perfect sense. If it does, great. If it makes some sense and you're kind of going along fine, fantastic. If you're lost, confused like crazy, well, have a quick look at it after class to make sure you kind of understand it. But I'm not expecting you to master this right now. The point I'm making here is, one, to show you binary search because it's pretty interesting. Two, to emphasize that algorithms are way more abstract, way more high level than the code. And you've done these algorithms before. Like I asked, who here has ever done a linear search through something before? Of course you have. Who here has ever had to turn to a page in the book and didn't start at page 1? Of course. You've done this before because you already intuitively know these algorithms, whether you like it or not. I don't care how good or bad you think you are at programming, you know these algorithms. It's just a matter of putting them into code. And that comes with practice. But the implementations could be wildly different. So different that we have an iterative and recursive one. But they're still doing the exact same algorithm, the same high-level idea. Is that the thing you're looking for? Yes or no? Look over here or look over here accordingly. That's the algorithm. I could show you with that textbook, and you know what I'm doing. You understand it. All right, cool. All right, what time we got? 54, perfect. Now to talk about trees. The remainder of this course is basically trees. We talked about some sorting at the end, but if we have time. Trees. This is the next big data structure. I know I just showed you a tree by visualizing those numbers with the binary search. Now we're actually going to talk about a tree data structure. We like trees. Trees are a generalization of your bags. A bag, each element had like one successor, right? an index bag. Index 0, index 1, index 2. Each thing had one successor. A tree is a little different. A tree can have multiple successors. But it kind of like depends. But we're going to get there. Trees. Sometimes we have data that's not naturally, obviously linear. There's no obvious sequential way to order the data. If I told you, like here, I mean, this is kind of an old lame example, but here's like an example file directory on a computer. You have like your C drive, and under that you have like documents, you've got program files, you've got like a music folder, whatever, I don't care. And then inside those folders you have subfolders, and so on. And I tell you, here, tell me the order of these elements, starting at the beginning and going to the end. And your natural response is, what do you mean? I mean, I could say, I could read the top and then go left to right, but is that more correct than doing it like alphabetically? Is that more correct than doing it in reverse? Is that more correct than starting at the bottom and working your way up? Why did I do documents and settings before program files? It's kind of all arbitrary, isn't it? If I gave you an array and I said, here, start at index 0 and go to the next thing, do you have any question? No, it's index 1. Why? Because 1 comes after 0, because that's how it works. Here, it's not obvious. You might come up with an idea, but I could tell you you're wrong and come up with some other strategy and you go like, oh, all right, fine. Because it's not obvious. But sometimes data is organized in this non-sequential way. Exhibit A. So let's talk about some tree definitions. Fortunately, these definitions tend to be fairly intuitive, so whatever. I'm never going to ask you like definitions of things on tests, right? But I might refer to them by what you call them, so you should know what they are. A tree is a collection of elements such that it is either empty, because you can have a bag that has nothing in it, right? And it's still a bag. You can have a list with nothing in it, it's still a list. You can have a tree that's empty, or it has a very special element called the root, from which descends 0 or many trees. You will notice that this is actually a recursive definition. Here is a tree. This is the root. I know it's upside down, deal with it. From it descends a tree. What is the root of this tree? It's this one. From it descends 2 trees. What's the root of this one? Well, it's this. This. And technically this has trees, but they're all empty. So this is actually a recursive definition, which is neat. I could give a recursive definition of a bag or a list, fine. But a tree, perhaps it's even more natural. A node is a single element in this tree. All right? The root is a node. Everything in between is nodes. A node is a very general term. And an edge connects nodes. So in this picture, the squares are the nodes, and the blue lines connecting them, not these black ones, they're just arrows. The blue lines are the edges. The root node is a special element. A tree can technically have 0 or 1 root nodes, but it can have never more than 1. A leaf node is the ones at the bottom. They don't have to be in the bottom row, it's a node that doesn't have any like children. An interior node is not a leaf. And an empty tree is one with no nodes or anything. Like an empty list, there's just nothing in it. It's still a list, but there's nothing there. It is possible to find alternative, I'm going to warn you. You can find slightly different definitions of trees if you go digging around, you could. We're going with this definition because it's probably the most popular and most universally accepted, but all the variations are remarkably similar. It'll just be like little nuanced differences. This is what we're going to go with. So here's some labeling. The black nodes are all leaves. That fancy, teal is the root. And everything that's not a leaf is an interior node. We're good to go. So a parent or predecessor is a node like above. A child is a node below. Any node can have at most one parent, except the root. How many parents does the root have? 0. The root is the beginning. But it can have multiple children. Any node can have any number of children by definition. A sibling, which is a word I don't think I've ever used outside of lecture, is a node who has the same, are nodes that have the same parent. Then you have like ancestors, descendants. These are all relative terms. Probably fairly straightforward, right? The root is an ancestor of all nodes in a tree. Observation, a leaf node can't have any children because then it wouldn't be a leaf node. Because as soon as it does, it's an interior node. It's not a leaf node. The root node of a whole tree has no parents. With the exception of the root node, each node has exactly one parent. A subtree of a given node is a child node and all descendants. So a subtree itself is a tree. So here, this is a subtree, this is a subtree, this is a subtree, this is a subtree. Okay? The subtree kind of is like it's a tree. Okay? A subtree is a tree. It has a root and everything. The subtree of this tree, labeled E here, has this many subtrees. And we can play this game all the way down to the bottom. A path is the sequence of nodes and edges leading from one node to another. So if I say, go from here to here, what would be included? Well, this edge, this node, this edge, this node, this edge, this node. A path length is, pay attention because this is often where people get mixed up, because you always end up asking, like, do you count the node you're starting at? No, the length is the number of steps you have to take. And the easy way to do this is, it's the number of edges. So from here to here, that's a length of 1, 2, 3. Count the edges. You'll never forget if you count the edges. And the height of the tree is the number of levels. Oh wait, maybe I missed it. A level of a given node is the number of edges between the root and the individual node. So what level is the root node? 0. What level is this node? 1. What level are these nodes? These nodes. Exactly. And the height of the tree is the maximum level. The maximum path length of all roots to leaves is another way to word it, but you can visualize this way. The path length between the two emphasized nodes is 3. The height of this tree is 3. Right? 0, 1, 2, 3. The tree with only a root is 0, a height of 0. A tree with only a root is 0, that should say height. And the height of an empty tree is actually -1, which is interesting. By definition, it is. The degree, or arity, I'm probably only ever going to use the word degree, is the number of nodes, given a node, is the number of children that node has. And the degree of a tree is the maximum degree of the nodes. So in this particular example, who could tell me the degree of this tree? 13? Nope. 4. It's not the sum. It's, you look at all the nodes, and you can get all the degrees of them all, but the biggest degree is the root node that has 4 children. So you always take the maximum, and then that tree has a degree of 4. And a binary tree is a tree where the degree is 2. No node has more than 2 children. Anyways, we'll stop here.